Okay, well, it's 2 o'clock, so we're ready for part 2 from Sasha here, so over to you.
Okay, so just, well, mostly the less people than yesterday, but there are people who were not yesterday. So just what we are doing. So we consider Topelitz determinant. And we are consider the situation when the weight, so we are looking for asymptotics as that goes to infinity. We try to prove the classical Ziegler theorem, strong Ziegler theorem, assuming that weight is in fact analytic and anomalous around unit circle. And we do it using Riemann-Hilbert representation for Topelitz determinant, which is just I have Riemann-Hilbert problem, which is a jump, which has jump on the unit circle with this jump matrix and with this asymptotics at infinity. And the relation of the solution of this Riemann-Hilbert problem to the Topelitz determinant, it is that formula. It's that formula above. More exactly, I have to introduce the family of Riemann-Hilbert problems. So considering the weight, introducing the gamma as a straight line in the space of weights.
I can't read your exponent to the last line.
And sigma 3. Okay. So again, so the summary is this, what I was talking about yesterday. It is just, so we have to consider more exactly, we have to introduce the family of weights, so the family of Riemann-Hilbert problems. And if we know its solution, then the determinant is given by the above formula. And we constructed solution of this Riemann-Hilbert problem, and that what we need to get the determinant as the first column. It is where the polynomials are. And so this is the formula for the y11. It involves, oh sorry, this is z to the n. Because here it is, yeah. Yes. So it involves weight. The leading term involves weight, and involves this Siegel function. So that I just written the logarithm of this Siegel function of its plus value. So Siegel. So if I'm originally I'm writing Siegel function with integration over the unit circle, then I calculate plus value. It means I take z and go to the unit circle. But since my assumption, my phi is analytic and the anomalous, it means I can prepare myself. I can just shift a little bit up the contour and then just put z on the circle. So z is on the circle. Integration goes around the C plus, which I call C plus, a circle which is a little bit bigger than the unit circle. So this is how you can, so this is C plus. Now what I already started doing, I started to calculate these derivatives. Okay, so this is a very simple. It is the prime means the z derivative. So this is the 3 terms, according to the Leibniz rule. And to t it is very simple. So I just neglect all these exponentially small terms. And then I need this combination. Then I need, of course, to analyze this combination, which is in my integrand. And after simple multiplication and simplifications, we get 3 terms. So this term is a leading term. It has linear dependence on m. and this is some combination of the term of the quantities. And these are two. Here it is wrong. It is, of course, we still have V gamma minus 1, V minus 1 to pi I, and then indeed this term. Okay. So we have in my integral, so logarithm d plus can be represented as a sum of three integrals. Well, asymptotics are to the exponentially small terms. So the I1, it is this n integral from 0 to 1 c p gamma minus 1 p minus 1 2 pi I d z d gamma. Also there is dz d gamma.
Yeah.
Afternoon exercises. Now, simple observation. What is V minus 1? You see, we have V gamma prime is in fact V gamma over gamma, the derivative, is exactly V minus 1. Yes? So, phi minus 1, it is just the derivative of V gamma with respect to gamma. This is how it appears, by the way, in that term. It is not phi, it is phi. And this is exactly the derivative of gamma. So if you have some more complicated dependence of the weight on some parameters, then we would have, instead of this phi minus 1, we would have the derivative with respect to this parameter. So quite general form. Quite general form. So this is the relation of resolvent to the determinant. Okay, so we can, and this is z, of course, we still have z, then 2 pi I. Z, 2 pi I, and z. Okay, so what we have here? Here we have, of course, d over d gamma. So this is d over d gamma logarithm of phi gamma. So this is just this derivative because of this formula. So the integration with respect to gamma and with respect to, so if I first integrate with respect to gamma, I just get logarithm. And this is the first term of the Siger formula. It is the average logarithm. Also can be sense, you know, if phi is so the first term gives us in fact the leading term of in Siger formula. Now the constant terms, they of course would come from here. So I erase this, so we kind of see that this is an logarithm phi 0, which is what we need. Let's consider the second term. The second term can be written as, of course, as again 0, 1. Now, logarithm of d plus, it is that thing. If I differentiate this with respect to z, if I differentiate this with respect to z, I would get I would get 1 over 2 pi I logarithm phi z prime and z prime minus z squared. There is no problem in differentiation with respect to z because z lives here, z prime lives there, so no. So this is again advantage of having quite analytic. So what we have, I can really write it down as a triple integral. So I have logarithm phi of z prime. Now this combination is again logarithmic derivative of phi gamma. This gamma, phi gamma, plus here phi gamma of z, and then we have z prime minus z squared, dz prime, dz, d gamma, 2 pi I squared. Such a term. This thing is symmetric with respect to z prime. So that was by the way 2. It means I have to kill this 2 and write d gamma of this. And then again I can integrate with respect to gamma. And I would get c plus logarithm phi, no gamma, z prime, logarithm phi, z prime minus z squared, dz prime, dz, 2 pi I squared. And now it is already very little left to see that this is this strong Seguin formula for the constant term. Because indeed, I can write it as say c logarithm phi of z, d over dz, logarithm phi of z prime minus z, dz prime, and 2 pi I, dz, 2 pi I. This is c plus. Now, z prime is bigger than z by absolute value. So if I factor it out and replace this denominator by geometric progression, then I will get this thing. Logarithm phi z, and here it's going to be d over dz, the sum of zk integral of logarithm phi z prime minus k minus 1 dz prime 2 pi I. And we are almost done. So once again, I just expand this z prime minus z into geometric progression. So it's going to be the sum over z prime over z over z prime, one extra z prime. So k goes from 0 to infinity. Those guys are exactly by definition phi k, Fourier coefficients of logarithm of phi. So what I get?
Is that 2 pi I at the end?
Huh?
Is that 2 pi I at the end still?
Yes, that is one more 2 pi I, which is also important. 2 pi I. And then here I would have the sum of what? Integrals of C. So this is already phi k I can write down, and I have the sum of C, and differentiate with respect to Z. It is k here, and logarithm phi of Z, Z to the k minus 1, dz 2 pi I. So this is V minus k. So this is the constant term in the strong theory. With the master class, there should be homeworks. So it is not very difficult to show that the third term is actually 0. Now this integration is actually 0. Again, you have to play. Again, this time you have to replace phi minus 1 by 1 over gamma, phi gamma minus 1. So this time it is, of course, you can not do it as a but like this. And then you will have two terms which you can first integrate with respect to z. The total derivative with respect to z. And one of them would gives you kind of the logarithm phi gamma around contour, and it is 0 because it's supposed to be that we always have 0 index. And the other term would be just 1 over phi gamma around, also 0. Very well. So this is how Riemann-Hilbert method produces the strong figure theory. Now let us do today. I want to try to explain how we get Fischer-Hartwig and maybe even how we get transitional asymptotics. So Fischer-Hartwig first. First Fischer-Hartwig. So we consider the simplest case. So this is the Fischer-Hartwig symbol, which contains CU part, V of Z, which again is assumes that this V of Z has Laurent series, which is in some analysis, which lives in some analysis around the unit circle. Then we have root singularity and, well, this is not that important, it is just n-jump singularity at 1. So in point 1 we have root singularity and jump singularity. So this is it's called Fischer-Hartwig symbol with one singular point. Yep.
Is that e to the minus I pi beta?
Yeah. Yes. So 2 alpha is supposed to be, of course, greater than -1, so that we at least can integrate. On the beta, a priori no condition. Beta can be any complex number. So now let us start doing our sequence. Going from y to t, it is exactly the same. Sorry. Yeah, going to y to t, it is exactly the same. It is y, because we just kill.
I just have a question. Z minus 1 is that's the absolute, right?
Absolute value. Yeah. That's yeah. So this is very big. So then I of course will replace it by the multivariate function. And so for t we will have of course for t we will have Yes, and for T, the Riemann-Hilbert problem would be just on the circle T plus T minus as before, the n phi z minus n T at infinity 1. Again, I can write the this great factorization. Try to prepare myself to to deformation of the contour to exponentially small, exponentially decaying terms. So it is just this. But now the point is that I want again to leave the unit circle. But to this end, we of course have to notice that now phi, although it is of course analytic, but here it has, so if you just do some simple exercise in the multi-valued functions, you would see that this is minus IP. That on the unit circle, this absolute value can be replaced by this times z to the minus alpha. And I assume that, as before, this is for the pulse of z, and this is cut for z minus 1. So the functions are supposed are fixed by this. So functions z to the, yeah, so that's what how they are defined. Okay. This is just identity. But now this means that instead of considering just smaller circle and bigger circle, I only can do the maximum what I can do. I can do this. I have a nail at point 1. And so what the best I can do, of course, I can go here. So this is my original. This is what I use when it's blue and green. So I can go this way, I can go that way. Going to my new point. So it means I can introduce now the function z. So the cuts are over there. So this is so I can introduce the function z such that it is so s. Now this is we go from t to s. From t to
Is
s.
the nail at z equal to 0?
Yeah, this is 1.
What? Oh, okay.
Yeah, and this is 0 is here. 0 is here. Yes. So here it is just t as before. It is t here also as before. And here, of course, it is in this area. It is 1 z to the minus t times phi minus 1 0 1. And here it is t times 1 z to the n p1. Everywhere here my functions are okay. So again analytically continue.
I'm sorry, I'm a bit, the line with the 5z with the z to the power, I'm a bit confused by that. The line above that where you dealt with the modular signs above. I think I must have missed
Yeah.
something. So you took off the mod sign, and then where does the new power of z come from? Oh, I'm missing something.
Okay, I can explain it, but I wanted to say. So it.
Compensate
The
the
Jamie, so in a sense, you can say that, okay, so this, roughly speaking, what is absolute value? Absolute value is z minus 1 times z bar minus 1, yes? But z bar, it is 1 over z. So it means that I have z minus 1 squared, z minus 1. Yeah, and then you have to check so this is the origin of appearance of this times z to the minus of. But then you have to indeed, so that's true. So the checking of branches is exactly as. Okay.
And also it compensates the cut from 0 to 1. Because originally
No, I don't.
yeah.
How? No, it doesn't.
For
No, it doesn't. No, it doesn't compensate. How it compensates? No. It has.
for the function z minus 1.
No, so what?
So you add
No,
z to
for
the
function z
one.
minus 1, of course, it is, as I said. So now I am saying, how those two functions are defined for this to be true. And the claim is that z minus 1 is defined with this set, with its cut, an argument of z minus 1 from 0 to 2 pi. And this function is defined on this cut, again, from argument from 0 to 2 pi. So the whole product is well defined, of course, on the cut from 0 to infinity. But it would have kind of still different values. On one is still be a nail.
No, what it says compensate means that originally you have z to the beta. Now you have a multi-valued function z to the minus half.
No, yeah, because, but this
But
is
then the
There's a
argument
minus-
says
there's a minus sign.
origin of this is because of that.
Minus sign, which
Yeah.
positive.
But again, so of course this function is there is this cut for this function, but I don't touch it anymore yet. It appears. So this means that my z. So I can now use. So it means that the Riemann-Hilbert problem for z is going to be this. So now it is just I would present on this picture the jumps. So this is the blue jump, this is the green jump, and of course I still have 0, pi, minus 1 on the circle. In the previous approach, exactly this jump was the main, it generated the leading term. So in the previous approach it was the main term. Now, of course, the situation is more delicate because now we can say that we have jump matrix exponentially approaching to identity only on blue and red, on blue and green, only outside some neighborhood of the nail. Z equals 1. It means that yes, I would still have, so my S, now I have to expect that my solution S could be represented by, which I still call, say, global parametrics, which is indeed the functions which just have a jump at only the unit circle, only on the unit circle, which takes care of this jump. Of course, there will be some problem at the nail with this, but I don't care, because I still will use this formula, this P only outside some small neighborhood. And of course, So this is going, this P would represent my function, my S. This P would represent my function somewhere outside of small neighborhood of 1. In the neighborhood, I will have to construct a local parametrics, P1. And what is the, what I would demand from this local parametrics? I would do 1, 2, 6. First of all, it would leave only, so its jump matrix should coincide with jump matrix of S in neighborhood, in this small neighborhood. So I want this parametrics to reproduce exactly the jumps on the small neighborhood. And on the boundary, I want this to match this P infinity. So on the boundary, I want to have this P1 uniformly represented as P infinity. 1 plus small, I don't know yet what's the estimation of it. And then goes to infinity here. And S. So that's what I need for P1.
So that neighborhood, the size depends on n.
No. It's going to be just fixed. It is 1/2. You can take.
Oh,
You can take 1/2. So this is again in PDEs. You have to work with the neighborhoods which depends, which is shrinking. But in ODEs, and it is much clearer, much easier. Okay, so first let's take care of P infinity. It is just we have to factorize this matrix with that phi, and it can be written by hand as before. The kind of the analog of the Ziegler function. I just write the answer, which can be checked by hand. So P infinity is, in fact, can be written as V plus. So I represent my V as V plus P minus. So this is a Lorentz series, and plus is a Lorentz series with a positive powers, including 0 power. And V minus, it is just the terms with the negative. Times Z minus 1 alpha minus beta E minus alpha probably plus. I then double check. So this is inside the unit circle. Minus phi minus Z minus 1 Z beta minus alpha. So let us do in 2 steps. So introduce this BZ, it is the analog of the Ziegler function. So that D plus equals D minus times phi. So that's easy to see that it is true. If you define this by Z, you get phi. And of course, this function is analytic inside of unit circle. It's analytic inside of unit circle because cut is from 1 to infinity. And here where we have the constellation of cuts from 1 to infinity. So for this function, the cut is between 0 and 1. So it is analytical set. And now P infinity, of course, is just as before, if I know CDO function. It is 1 if z is greater than 1 and 0, 1, negative 1 if z is less than 1. So this is about P infinity. So now I'm afraid that all the remaining time we will spend on constructing local primitives. Because I want really to do it slow, because it is not just some technicalities. It is almost each step. There are several steps which are very conceptual. I will be able to construct it explicitly, and I will use something relatively unexpected. So I will use the monodromy theory for hypergeometric, confluent hypergeometric equation. So once again, I'm going, so what we are doing? Once again, I'm going, so this is, I consider, now I am in U, so it means I'm just in some neighborhood. And then in this neighborhood, what I do, because I want to simplify, I want to undress, as we call it, the Riemann-Hilbert problem, the original Riemann-Hilbert problem. First of all, I can get rid of phi. So I can go to z till s tilde, which is s times phi sigma 3 over 2. So what jumps I would have? Don't worry about what is going on the boundary yet. So we will then take care about it. So first I'm concentrating on take care of the jumps. So then if I take it like that, I would just get rid of all the, and phi was there. So what I would get, I would have this thing. I would have still my unit circle. This, and this. So these are my lines. 1, 2, 3, 4, 5, 6. But now, as you know, so now we have to add 2 more, because now my phi is going to jump. My phi is going to jump here. And so what the jumps are for S tilde? For S tilde, of course, I would get here just 1 to the Zn 1. For those guys, I have 1 to the Z minus 0, 1. This is this. Here I would have just 1, negative 1, 0. 1, negative 1, 0. And there is a price to pay. I have jumps here. It would be diagonal, of course. Would be diagonal. It's going to be, if you look at carefully, it's going to be such a diagonal matrix from this side, and pi alpha plus beta on this side, if I'm not mistaken.
It's any
Specific
specific
reason
reason
behind the sound. Huh?
your all curves going outwards to infinity.
Not yet. No. Now
But
I'm
the new axis goes in opposite direction.
Hmm?
It's a specific reason.
No, it is. I don't know why I chose it. Why I chose this way. Not sure.
So,
Well, you always can check the direction.
The pluses and minuses are.
Yeah. You just should replace the jump matrix by it inverse. Very well. Now it is a time to become really local, to introduce local variable. from, as usually, from Latin to Greece. Is it xi? Is it xi?
Yes.
It is xi, yes.
Yeah.
Okay, so let's go to this variable. Then the whole picture, of course, will straighten it up. So then, and let us call the model problem, which we will find kind of the image of S tilde on this zeta. Let me call it F naught. Not because I'm going to do three more steps. F naught of zeta. And of course, what is just? It is just this. Now it is 0, of course. I think it is a straight line. So just those rays. So of course, unit circle becomes the imaginary line. The real line becomes real line. But those guys are just chosen in such a way that here I have straight rays. So this is a good holomorphic map in the neighborhood of z equals 1. So this is a conformal change of the variable, local conformal change of the variable. When I have my here it was the other way around. It is z to the n, z to the negative, and they are outside of the unit circle. So this is e to the minus zeta. So again, exponentially small outside of 0. E to the minus zeta. E to the, it is still alpha plus beta sigma 3. This is still IP beta minus alpha sigma 3. And this is 1 e to the zeta. 1 e to the zeta. And here it is again 0, 1, negative 1, 0, 0, 1, negative 1, 0. So this is my local, and now look, on z plane I'm in a small domain, in a small circle around 1, in a small neighborhood. After this change, you see large n. It means that my small hood becomes in the z over there. So in fact, it is at infinity. So in fact, it would be, I would consider this problem posed on the whole zeta plane. And the only things which I will have to get somewhere at some point, it is to see what sort of the asymptotic at infinity I have to impose on this function. And of course, the reason for that would be that I would use this phi naught to build my local parametrics. I want to have this. And this is what we will see. This is what would dictate me the condition of infinity, which I have not yet formulated.
So this is what in asymptotics is called the inner variable. Inner asymptotic.
Yes. So in the yes, of course, in the language of WKB method, this is of course we are talking about some inner asymptotics, inner variable. So it is inner variable. It is not exactly a turning point, but it is yes, it is a single point. Okay. Now I would like to get rid of as many rays as I can, because it is I want to get as many rays as I can. Because what is important, you see. So first of all, I can get rid of this thing. So it means I go from, I maybe even continue to be here.
Can you do it sequentially, one at
Huh?
a time?
What?
Can you get rid of one at a time, sequentially? By getting rid of the jumps one at a time?
Build one at a time, yeah. I can, of course, write long, but it is
But it's
better
not
to do
convenient.
one at a time. So my first would be to go from phi dot to phi 1, which is just phi dot on the right hand side. I have to multiply it by 1 negative 1 0. Just this one. And here identity on the other side. So by this simple trick, of course, I get rid of this. So for phi 1, it is this. The price to pay it is I switch those guys, which are good. So we will begin to see stocks, stocks picture, of course, very soon. And minus appears because it is not exactly sigma 1, it is this. So I would have this. And switching of this diagonal matrix. So this is a new thing. Very good. My next, I get rid of. I'm going to get rid of this thing. I'm going to get rid of this thing. So it means I'm going to go from phi 1 to phi 2 in such a way that I would have. So I only change my function in these domains. I just introduce my phi 2 will be everywhere what it was phi 1, except that here it would be phi 1 times this exponent, and here it would be phi 1 times that exponent. This would mean, so maybe I will, this would mean that I would get rid of this jump and would have, so let me restore it. I'm sorry, let me restore it. I wasn't, so this is I pi beta minus alpha sigma 3. Nothing here. So more exactly, I introduce phi 2, which is, let me write it. So it is phi 2 times this phi 1 times this matrix on the whole, this quadrant. So e to the I pi alpha plus beta sigma 3 everywhere here. And e to the minus I pi beta minus alpha sigma 3 everywhere there. Yes. Then I would get rid of those. Indeed. I will change this thing because they are going now, and I will change just to write it precisely what it is. So I would have here, instead of what I had before, I would have one e to the minus 2 I pi beta minus alpha e zeta xc, and here it is because that's the conjugation with this matrix. We just produce this term. And here I would have 1 minus e to the minus 2i pi alpha plus beta e to the minus zeta. That's what I will just change it here. And of course I will get one more cut. Because those guys would meet each other on the negative matrix, and this would create just diagonal. So this is phi 2. Now the final phi 3. Now the final phi 3. Okay, let me use this. The final phi 3. The final phi 3. I go from phi 2 to phi 3 of z, which is going to be phi 2. So what I'm going now to get rid of, I'm going to flip those two rays to the real line. All this is very innocent operation because I only, of course, whatever is going on at infinity, I would rather with my not to violate the, you see, this matrix goes to identity at infinity exponential. So if I, but this is a good area, so I can really, how to, what's the word? I will do this. Okay, so what it means? It means that on this part, I have to multiply it by that matrix by 1. On this part, I have to multiply it by this matrix. This is in this part. So on the positive real line, they just meet, they just add up those things. And of course from here also on this part, I have to multiply this by 1 minus e to the zeta on this part, and by 1 minus 2i pi beta minus alpha e to the zeta on this part. So what's the problem I want? So now it's going to be my final. So this is a phi 3. After that, my phi 3 problem would become I just write it. So this is what I get for phi 3. And of course I can, whatever I can do for phi 3, whatever I can do for phi 3, of course I can go back to my very first it is. And the problem is this. So this is the most economical way to take into account the Poincare index 1. So you have just e to the zeta. There is only one prime. So I have, and you cannot do better. So this is the last. So this is the most final e minus 2 pi I beta, it is still, and here it's going to be, let me introduce new, this is S1, this is S2, where S1, of course I begin to use the Stokes phenomena notations. But there is no any equation, so this is just the combination, the sum of those guys. Minus 2I, I pi alpha plus beta, sine pi alpha plus beta, and S2 is minus 2I, pi I, alpha minus beta, sine pi alpha minus beta. So these are jumps. And now I'm going to close everything. So what I'm going to have at infinity for this problem. This is the first time I'm going to formulate. But before, okay, first of all, we have this singularity here. This, of course, I have singularity. If we trace how it appears with all my multiplication by phi's, it would be not very difficult to believe me that what it is something like matrix, and here it is, zeta alpha plus O C minus alpha, and similar things everywhere. So this is a combination of C alpha and C minus alpha. Whatever has a negative or positive real part.
Near C equal to 0.
Huh?
Near C equal to 0.
What? At Z equals 0, yes. So this is, of course, I have now to describe what is going on at 0. So it is at jumps. Now I want to describe what is going on at 0 and what is going on at infinity. And now this is the things which I have not motivated yet. I am claiming that at infinity I want this to have the following.
But the matrices will be different depending on which direction you approach 0, right?
What?
I mean the jumps. If you
Yeah, but you see, because it's all, I will actually make it more precise in a few minutes, of course. Yes, you're right, absolutely.
So is that the matching condition?
Yes, this is a matching condition. You see, if you allow me to skip it, I would rather to skip it, because there is another logic. You have to impose the condition which would allow you to solve it. You have to impose the condition. There is only one way to choose behavior at infinity, so that you really would have a well-posed problem, which would have solution. And then you have to check that with this infinity, you would have good matching condition. And this is what I claim, that with this thing, if I can take P1, I can choose P1 of Z can be indeed defined as some matrix, some Z times this my phi 3 zeta Z. Of course, a lot of this, I mean all the steps back. So in different part, I would have to multiply this by not on this. So that would be, this thing has the same jumps as S infinity, as S tilde. So to go back to S, I have to multiply it by sigma C over 2. So these things would going to have exactly the same, already back in the Z plane, would have exactly needed jumps in U, in the neighborhood. And my claim is that exactly with this choice, I would be able to choose E in such a way that I would have E galomorphic function, which it would not violate. It would not violate the. It would not violate the jump condition in such a way that I would have matching condition. For instance, again, the choice of this E depends. So if I am, for instance, if I am, well, this is my original. This is my original part, which is not affected by any changes. For instance, in this part, I can choose E as P infinity of Z, C of Z beta sigma 3 times phi sigma 3 of 2. I kill two birds by this formula. So, first of all, this thing is indeed going to be golomorphic. At least it would have just the Taylor series over the positive powers of Z minus 1. So all the branching would cancel. And this is because, and this is why I need the Z beta to cancel branching from P infinity. On the other hand, when I put myself on the boundary, then I can replace phi by its asymptotics. And of course, all this cancel, and I will get just P infinity, just P infinity. Again, if you don't quite follow me, it is the statement that with this condition of infinity, I will be able to arrange matching condition. Now this is a completely posed problem. So let's try to solve this problem. So now I am going to show how I'm going to solve this problem. And this is where I'm going to use special functions in. I believe it is not quite used in this way before we started with Painlev.
So the origin is probably because you have 0 and 1 single point, and that is why you end up with geometric functions.
No, it's going to be. No, this is not 0 1. Look, now 0 1 already disappeared, so I have just 0 and infinity, and 0 regular point, infinity irregular. So that is a confluent hypergeometric function. So more exactly, what we do? More exactly, we do this. Psi function. Let's move dependence on BC to infinity. So where is standard 3? Times sigma 3. So let's do this. Then, of course, my psi would have jumps which are all constant. So this is jumps for psi. Then it is at infinity psi now behaves has regular singularity. As this is at infinity, everywhere at infinity. And at 0, and this is what you already said. In fact, I can specify. Now I can specify. Sigma 3, some Cj. So I claim that I can choose in these 3 domains constant matrix C, so that this product would have exactly these jumps. And so my function psi differs from this product by some golomorphic function. So this is a representation. This is a kind of codification of qualification of the singularity of zero. So once again, I claim that this is a sort of exercise. Can we consider that you can choose C in such a way? You start with some C equals 1, and then you just choose it according to, and of course you take into account that this is a good test. In other words, the product of those three matrices is not identity. So it means that there is a singularity. And the singularity is exactly this.
So just checking one
Yeah. So if I have some Riemann-Hilbert problem posed on the contours with that intersection, if I have in each node no monodromy, then there is no singularity. But here there is. And now, of course, the way how I am solving it is of course to consider this logarithmic derivative of this psi. It's going to be a rational function because it's never, all the jumps are constant. So it is a rational function which has simple pole because of this at 0, and it has constant at infinity. So in fact it is what it is, minus 1/2 sigma 3 plus I naught or sigma. Where of course I naught it is psi hat of 0 alpha times sigma 3 psi hat 0 1. This is I naught. And that's it. So it means that my solution must satisfy rational equation. I can kind of calculate. So A naught, because of this A naught actually can be written, it must be something like delta minus delta trace is 0 BC. Moreover, if I take this expansion, so this I come taking this expansion into this equation. If I take expansion at infinity, I can calculate the diagonal part of matrix A naught, and it's going to be beta, my beta. So this is, it does not follow from here. It follows from substitution of this series, of the series at infinity. And finally, of course, the determinant is alpha, so I have beta squared, BC equals alpha squared minus beta squared.
Some kind of accessory parameters. Right?
There is no accessory parameter.
Because there are no.
There is no accessory parameters. So we will, of course, here it is. So when I go to the second order differential equation, there will be no accessory parameters. That's the whole point. That is a very interesting thing. It is when there is a second order differential equation, in the second there is no accessory parameters. Simultaneously, it means you can solve it in contour integrals. So if all parameters are defined by the exponents at regular points, it means that. But if at the very moment it appears, you cannot. But this is not a theorem, it's not proven. You cannot solve in contour integrals Gain equation. But you can hydrogenetic equation. But here you see, this BC, it is kind of the fact that there is one parameter, it is not a big deal here. It is.
No, I mean that they will be defined, of course, because.
Yeah. That's the point. That it will be absolutely
but
defined.
I mean, it's some kind of analog of them.
No, yeah, I would rather because it is in a sense you see because there is a monodromy data. So there is one-to-one correspondence between this B and C and two monodromy data. There is no place for accessory parameter. There is no place for the monodromy deformation. There is no place for accessory parameters. That's because we have to talk about the whole monodromy data. Anyway, so now So this is the element of the general theory of kind of the equation with rational coefficients. So how can I use this general theory to construct solution of this thing? Of course, I have Stokes phenomenon. So forget about this part. Just look at this part. So we look at this equation and we appreciate that it has three canonical solutions that behaves as E minus zeta2 over sigma 3 in three sectors. This is k equals 1. It is argument z from minus 3 pi over 2 pi over 2. This is the biggest sector when I can fix one. It has only one Stokes line.
What is the k? Oh, you mean each of the.
Oh, sorry. Minus 3 pi over 2. So this is for the k equals 1. This is for the first canonical solution. The second canonical solution fixes this argument z greater than minus pi over 2, less than 3 pi over 2. I have. And finally the third one, it is back, but on the other sheet. It is here, this is k equals 2, this is k equals 3. Argument zeta, not z. Greater than pi over 2 and less than 5 pi over 2. So this is the general theory tells us that because we have this behavior, there are these three sectors. It doesn't matter even about all this. So this is a absolutely kind of, so if you have, I can have the whole line.
So these are solutions to that differential equation.
Yeah. Each of them is solution of.
But there is a relation between those three.
No,
right?
of course, and this is why I can use it to solve my problem. So then I'm describing the Stokes phenomenon. So psi 2 equals psi 1 times S1. And psi 1 equals psi 2, psi 3 equals psi 2 times S2. Those guys have the same asymptotics on this, and from minus pi over 2 to pi over 2. This is a general domain for them. For those, general domain is this. So this means that S1 is 1, S1, 1, and S2 is 1, S2. I'm not claiming that this S1, S2 is what I had before. So right now it is again, I don't look at this part. It is just there are such an S1, S2 which are generated. Of course, they're not independent. There is a cyclic relation between, because there is also the canonical behavior at 0. You have to connect it, and so there is a cyclic relation. And from this cyclic relation, we would get, in particular, this formula. Cosine 2 pi alpha minus cosine 2 pi beta. Very well, that's it. So, and this is usually why I'm not saying that we have here accessive parameter. Because the whole monodromy data parameterized by those two parameters, Stokes multipliers, which are related by this if I fixed exponents. And I also have in my singular data, so to say, my equation have two parameters, BC. So this is in a sense, this is the direct and inverse monodromy problem, which can be formulated, of course, for any equations. But this, the great thing about that is that I can actually solve this problem explicitly. This is a manifestation of special functions. So the point is that I now of course I want to have S1, S2. I want to construct, I want to choose my A and B in such a way that I would, so this means direct that A and B in such a way that my S1, S2 are given by those expressions. So this is, I want to solve inverse monodromy problem explicitly. And I cannot do it for kind of the generic systems, but for all systems which can be associated with the special functions, I can do it. This is a sort of the answer on the question, what is so special functions? So okay, but there is of course an extra very important bonus. I can actually write down the solutions of this, and I have not said how I'm going to build. So this my psi to solve this is going to be constructed out of just psi 2, psi 3, psi 1, and that's going to be solution. So if I have canonical solution of this system, I put this. I have solution of this Riemann-Hilbert problem. Now the great bonus is that not only I can characterize explicitly my B and C in terms of S1, S2, I can write the solutions as a contour integrals. And the point is that when you go to the second order differential equation, okay, just trivially excluding the second components, you get, of course, up to the trivial changing, up to the trivial the confluent hypergeometry. Even directly, you get just second order differential equation with linear coefficients. It means that you know nothing about confluent hypergeometric functions, but you can just go ahead with the Laplace method and solve it and write it. And then having contour integrals, doing the steepest descent, you of course can relate your AB to S1, S2, and as a result, but also get the solution of those contour integrals. So this is how it goes with the Fischer-Hartrich. Of course, then this would give us a solution for orthogonal polynomials, for the corresponding orthogonal polynomials, and then we have to use that formula, which is now technically is more involved, because now I have to actually how I get determinant from again I have to write some differential identity which I then would integrate, and here I have to write something with respect to alpha and beta. So just go from alpha equals 0 when I have just okay to the alpha equal 1. So it is not a trivial matter, but can be done. So now I still have 10 minutes, I think. Let me just outline what to do with the transitions. So how we manage transitions. So here we just look at here is we take the family of symbols that connect Seeger symbol and Fischer-Hartrich. And Fischer-Hartrich. Let's consider this z minus equals to minus t alpha minus beta, z minus alpha plus beta, again some just to get final formulas, and the Seeger part. So T is frequency. So when t is is not 0, so what I have, this is a unit circle. I have 0, e to the minus t, e to the t. So this is the cuts for those guys. So this is a figure symbol. Everything is great. When t goes to 0, I get okay. No, there is no way I can I skip this, I skip that. So, just, I'm still doing more or less the same. But now, my picture is this. So I would have something like this. This is e to the minus t, e to the t. No, what I'm saying. No. Yeah, this is e to the t. So now it is not the nail kind of, completely, but this is a shrinking thing. So it means that if I consider again outside, it would be the same global parameters. But inside is going to be something which now has two points. Simple. It is indeed. Again, I would just do the same local. And again, I would have here all these phi's, all these my triangular matrices everywhere. But then, after looking carefully on so the result, let me just formulate the final. So if you're just doing, again, if you're just doing according to everything according to my previous steps, you really does not need to invent much. You will end up you see, with this changing of variables, my points e to the minus et becomes minus nt. And point e to the t becomes point nt. And this is a good combination to consider some kind of the double limit. You push n, t goes to 0, of course. You push n to infinity, t goes to 0, but this is going to be your natural scaling parameter. It's called x over 2. So this is my natural scaling parameters. When it is bounded, it means that nt is bound. Or if I want to match to asymptotics, I would just have to put x is to 0 or x to infinity. And to the standard ideology of transition asymptotics. And now what I would have for the problem. For the problem, I would have this. So eventual, final psi, the analog of the problem for psi of zeta, I would have this. So this is again kind of 1 e to the I pi alpha plus beta. This is going to be just 1 1, 1, 1, 0, 1, 1 minus. Oh, this is called, no, this is, yeah, this is minus 1, 0, 1, minus I top, alpha plus beta. And the jumps from X over 2. And here, of course, again, my okay. So so this is jumps for function what was psi before. Its behavior at infinity is the same. Its behavior at infinity is the same. Its behavior at infinity is the same. I just wrote it inside. But what is important to have now, instead of one regular point, regular singularity is 0, it has two. Those 2 points. So that's the result of whole phenomenon. It will be some holomorphic functions around x's, and of course c minus plus x over 2, beta plus minus alpha over 2, and again some CJs. This when zeta around plus minus x over 2. So again, the whole effect of transition, it is to become and now what does it mean from the point of view of differential equation? Now again, I can write, of course, differential equation for psi. It would have, of course, what I had before, but instead of 2, of 1 simple pole, it would have, of course, and now we indeed have, well, accessor parameters, and I cannot get rid of x. X is a parameter. X is a variable which you cannot get rid of. You cannot kill it by any changing of variables. You can move it from here to there, and that's it, what you can do. And actually, this is what usually people do. So in fact, my function psi is going now, of course, to depend not only on these fixed parameters alpha, beta, but also on x. So I have depends on zeta and on x. And x is a scaling parameter, so I want to see how it indeed depends on x. But with respect to x, nobody depends on x. So it means the Stokes matrices are independent on x. So dependence on x is isomodromy dependence. And it is known which it is. So this is a Lux pair of integer 5. So this is, of course, a Lux pair of integer 5. It was kind of classified many years ago by Jim Benil. So this is one of the kind of integer 5 and you cannot write any more explicit solution, which again, it is not a theorem. You can explicit it in terms of the contour integral solutions. But you still, since there is this x, you can pose the question dependence on what is going on when x goes to the critical points of integer 5, which are 0 and infinity. And this you can do, kind of analyzing this Riemann-Hilbert problem asymptotically, using again steepest descent already for this. And you indeed can see, you can get an answer. I will just, we're already 1 minute above, so but the answer is long. But it would be very good. It would be really match CGO asymptotics and so and Fisher-Hartley asymptotics through indeed PNDV5. And important, of course, for this matching that we would know for this PNDV5 how it behaves at 0 and how it behaves at infinity. And this is the generalization, as I already mentioned, that the first when v is 0, alpha is 1/2 and beta is 0, or the other way around. When the alpha is 1/2, beta is 0. That is exactly the symbol for Ising model. And T, it is related to the temperature. So it means that we have this, and this is what was indeed done by McCoy, Tracy, and Wu. This sort of, well, not using these techniques. Yeah. But that was the first time when, as I said, in the appears in applications. The second time, because they themselves refer to the miles, to the works of miles on actually on diffraction. And then actually took it from him. Probably Peter knows more about this history of issue. But this is what Tracy says, that yes, that when we ask him, how do you know that this is miles? So they saw it in miles. That's probably kind of, I don't know, once again, Peter should know better, but to me it is the first application of Painlev, probably it is in these miles. But the second and the third, the second was in this this McCoy Tracy Wu, and simultaneously, by the way, it was also found in Painlev 2 in as a transition asymptotics in KDV by Topelitz and Sigur. And they have not produced the connection formula for the phase. Yes, which was actually first rigorously established, I believe, by Peter with MacLeod. Okay, the history. Thank you very much. So this is.
Thank you very much. Do we have any questions?
Just a small. You generalize it some kind of big gap between the previous solution and the second one. But if you put a coefficient, why you put it symmetrically? This ET and E minus for certain reason, or just for
no, but
it's elegant?
Not to introduce just two parameters.
Yeah, but then you can put you can study the limit like t goes to infinity, and then one of the branch points goes to 0. The second one will stay, and then you probably have
to have good material. So it is the whole area still. You know, first of all, it is the simplest case where we have just one merging of one singularity.
No, what I'm saying is if you put the coefficient and let one of them go to infinity, then have z to the alpha minus beta, it will be branch point at 0.
No, but
another one will be.
I don't know, but then it would be always singular symbols. So what it is just, it is not transition. If one point goes to infinity, another to 0, then what? Okay, you have to somehow renormalize because infinity, everything goes to infinity. But it is the symbol stays as a good symbol. I don't see big. The merging is indeed this when you change. Also interesting thing is when you consider two Fisher-Hartley singularities and they merge. There is a lot of application. Actually, it was done by Igor Krasovsky and his student. And then his student actually considered several. And just it was very interesting result because we thought it would be very difficult to take it result, but somehow it is, he managed this kind of multi-particle system. Yes, so that is, yeah, so there are still a lot of open questions, but they are technically really very tough. And one, but some of them has very good motivation. So it is indeed in the works, for instance, of Keating and Federer, in their study of this application of random matrices to number theory and to again statistical mechanics, this situation when they have merging of singularities appears, and you have to know quite delicate things about it.
In many of these problems, you have this Stokes constant, which you can't do explicitly in these cases. So could you use the Ovidie question and one? They have a method, a adiabatic method of finding the Stokes constant.
We already discussed it. Maybe we will continue to discuss it because I have not done it yet.
Did you see the paper?
No, I saw the paper, but it is only. But again, we already had this conversation. You mean the paper when it
So
is
there is
for Painlev one for
no, they apply it for Painlev one.
yeah
But the
for three truncated solutions.
Yeah.
To
But
calculate
this
this constant.
This is based on tran series and also
No, I know this result.
adiabatic idea, and you can actually trace around.
I know. Okay, but at least, but strictly speaking, second again, it was already pointed it out. I would rather do this calculation, this particular one constant for three truncated solutions. It is a good that they've done it, but this is from this point of view, it is rather simple. So it would be, I would be really impressed if they can reproduce, for instance, a Abelowitz-Sigur connection formula. They say, and you said that
No,
you may, but read it down.
It's a
That would be great. So if you indeed finally it is written down. So I asked Kostin to do it 20 years ago. No, but of course this calculation of constants for three truncated solutions was, but even more important, what they did, I believe, with you, it was the proof of the Dubrovin conjecture. That was, of course, that was where we a little bit cannot do. So this is a Riemann-Hilbert approach, very good asymptotically, very good for connection formulas of asymptotics. To say something about global, about finite domains, it's not much. So this is, and so so far there is only one proof of the Dubrovin conjecture about the absence of the poles in the whole sector. It is which was obtained by Kostin and the third guy.
One of our students.
Okay, well, let us thank Sasha once more for a fantastic lecture.
Thank you.